Welcome back, literature fans. Today we hope to do y equals x to the third using the Weilberger setup. But I'll review my setup first and then I'll switch over to the Weilberger setup. So y equals x to the third, and using my setup, something like this, and I'm using notes so that I won't make as many mistakes. So here's how you set up mine. 0a, 2a. So these are equal portions. And of course, if you have 2a and y is x to the third, then you need 8 partitions, right? Because 2a to the third is 8a to the third. Here's 0, here's a to the third. So we have something like this. That's our x-axis. Our t-axis is here, translation, 0 minus a plus a. Here's our curve itself. And what do we have? We have these nice partitions. So with y equals x to the third, but we also know that x equals a plus t. So y equals a plus t to the third. And we crank that equals a to the third plus 3a squared t plus 3at squared plus t to the third, which comes from Pascal's triangle. There, that's that. That's binomial expansion. Okay, this is a linear term, which is right here. This is that's our constant. This is our linear term, 3a squared. This is a third, right? This is 3a to the third, and this is a to the third. When you plug in t equals a, that's the values that you get. Those are the proportions. And this all adds up to 8a to the third. Pretty simple, huh? Here's Norman Weilberger's setup. Y equals x to the third. Again, we're going to have our chart over here. And we're going to draw it similar to what I did before. Right, except this one starts 0 to 1 and to 1 plus c on the x-axis, which translated to the t-axis becomes 0c minus 1. Okay, we need still 8 partitions here, and you'll see why. Alright, this is our 1, 3c. If you plug in t equals c, you get 1. In here you get 3. There's our tangent, by the way. Then you get 3c squared. You plug in that. 3c squared. And then finally c to the third when you plug in t equals c, which is over here. C to the third. So you still get these ratios 1, 3, 3, 1. But it's a little bit different from what you saw just earlier. Okay, we'll set it up for slope at, well, at t equals c, and then we'll set it up slope at t equals 0, and you'll see how quickly and easily we get our C3 factor, which is what we're after, right? So slope at t equals c, right here. So from the big picture, from the x point of view, that'll be at x equals 1 plus c, right? And that's also rise over run, this characteristic diagonal, times the invariant. What's the invariant? C3, the unknown. So let's write that down. C3, and again, don't confuse the C3 with a C. I use C3, C4, etc. Those are my invariants, and I want to be consistent with that notation, but this notation is what was used by Wahlberger, 1 plus little c, so let's just make it big C3 so it really sticks out. Is that better? Whoa. Okay, this C has nothing to do with this C. Okay, that's a C3 times, well, it's rise over run. That's our diagonal slope. Well, that's 1 plus c to the third times it's over 1 plus c. Rise over run. Well, maybe I'll stick with it. I'll clean it up. Okay. Whew, making mistakes again. And that equals, it's the individual slopes at each of these. This one, there's a component over here, the quadratic, and then the cubic. You got 4 components, so it's at t equals c, so the first one, that's just a 0 because it's flat. It's constant. Plus, well, linear, you can see the slope is 3, so it just put that down, plus 3. Plus, what about the quadratic? Well, we know it's c2 times, which is what? 2 times 3c squared over c, right? 2, because it's the second order, times rise over run at t equals c, so that's 3c squared divided by the run, which is c. Alright, plus, so we're here now, the cubic, well, that's our unknown, plus c3, and I want to make it a big c3 so you never confuse it, times well, rise over run, right? So it's c to the third over c. So let's clean this up a little bit. We get c3 times, well, this is really 1 plus c to the second power because we reduced it. Yeah, 1 plus c squared. The third power divided by to the first 1 power, that's going to give you a second power. Pretty simple. We reduce by 1 power when we do slopes. When we do areas, we increase by 1 power. You can already see the inverse effect. As I was telling you, that the slopes in the areas are very much related. And you're seeing it, and you will see it. Okay. Well, that equals this whole thing. 3 plus 6c C plus C3 times C squared. And this are different variables. I should make a big capital C so you don't confuse it, right? Okay. All right. Let's crank. So C3, and this is second order now, right? So these are the factors that you use. So it's just 1 plus 2C plus C squared. You've seen that before. That equals this whole thing. 3 plus 6C plus C3. And you have 1 plus 2C equals, I can factor a 3 out of it, and I get 1 plus 2C. And immediately, this cancels this. C3 is equal to C. C3. C3 is equal to 3. That's evident. But you can also get the same information by collecting your powers. This is C to the 0 power, right? And this is your C to the 1. In other words, C3 times 1 equals 3, right? From here, you collect these, and then you collect your C's. This is C to the 0 power, this is C to the 1 power. Everything has to, you collect the C's with the C's, C squares with C squares, etc. So, okay, immediately you get C3 equals C. If you collect your C's, well, you get C3 times 2C is equal to 6C. And the C cancels out, and you can see again, you get redundant information, but again, you get C3 is equal to 3, because it's 6 divided by 2, right? So, you get that right away. That's a T equals C. And it was a little bit of a slugfest, but you know, we got it. What about if we do slope at T equals 0 right here? Now look at this. At T equals 0, you have to ask yourself the question, out of this equation that we have, which one of these, or do all of them contribute to the slope? How much does a constant term give you as far as slope? Constant term is always 0. 0 slope. It's flat. The linear term, that's always going to be 3. Hey, how about that? What about the t squared term? You know, you've seen this before. At t equals 0, what's the slope right here? Guess. It's a 0. T third. T third is also 0 because it comes right underneath, right here. So everything is 0 for slope except this one term, this linear term. That's the only one that gives you slope. And so, like that, you get it. So our slope, you say, okay, from the x point of view, right, it's C3 times rise over 1. Well, that's 1 over 1, right? That's just 1 over 1. That's just 1. That equals your contribution. Constant 0 plus, this one gives you how much? 3. You can say it. That's all right. 3. Plus This one gives you
0.
0. This one gives you 0. Look, C3 is equal to 3, just like that. Now suppose I had fourth power. What do you think this would be? You know, you have 1, 4, 6, 4, 1. This term would be a 4, right? Well, everything else, the slope would be 0. The only one that's giving you slope is this linear term. So C4 is 4, right? Just like that. What if you have C to the n? So that was pretty easy. Using t equals 0 in Wahlberger's setup, we just get it like that, and we even get the slope for, you know, c to the n. C to the n equals n. That's better than, you know, wow. Okay, let's do the area. Area, right? Okay, I'm gonna have to do some cleanup. Area, in particular, you want to find the k factor, K3, using Wahlberger's setup, right? K3 equals question mark, which we already know is going to be 1/4, but we'll prove it. So area. Area, okay. So the area is, well, here it comes. K3. Don't have enough room here. Okay, area, we're doing area. K3 times rise, 1 plus c, third, times run, 1 plus c, right? That's the area of this big wedge that you see over here. And that area consists of a couple of small areas. 1, 2, 3, 4. That's these components plus this one. That's the fifth one. So let's go after it. This one here. That equals, well, that's our unknown on the x-axis, right? That's our K3 times, well, what is that value? That's rise times run. It's just K3, 1 times 1. Right? Plus the constant, this term here. Well, that's this term here. That's rise times, that's 1 times c, that's c. See it? C, that's the base, and what's the height? It's 1. So it's just C. Plus, this is our linear term, so the k factor for that has to be 1/2, right? We already know that, right? 1/2 times height times base, so it's 3c times c, right? 3c is height, c, and that forms a box, and times 1/2, that's the k factor for the linear term. Plus, for the quadratic, we know it's 1/3 times, what's the height? When you plug in t equals c, you get 3c squared times c, right? Rise over run. Plus our last term, that's our unknown K3 times rise over run. That's c to the third times c. Welcome back. we had some battery issues, so we had an interruption, but it allowed me a little bit opportunity to think about these things. And so let's review where we left off. And essentially what we have, we're doing the area. And there are 5 areas, little areas. This one. And then you got your 4 areas. Constant, linear term, quadratic term, and cubic term. And it's a reminder of what we're doing here. Basically, we're finding the areas. So here's our constant term. We put a box around this thing and multiply by k0, which is 1. And the base is always c, the height. You plug in t equals c, you get the height for each of these components. Plus, this will be a k1, which is 1/2, right? Times the box, which is 3c times c in this case. You see it? You plug in t equals c, you get the height and the basis from 0 to c, and multiply it by an appropriate k factor, k1, because this is the first degree, plus, well, this is a second degree equation, so we're dealing with k2. All of these we know at this point. The only one we don't know is k3 until we derive it. So it's k2 times the box, base times height. You plug in t equals c, you get 3c squared. Plus, here's our unknown, k3 times the box. And that kind of looks like this, right? I'm just matching it up. There. There. And this one, that's just this box times k3. Okay, so that's where these things are coming. Similarly, what we did for the slope, tangent slope, was we took the slopes of these, and that'll be a c0, which is 0, times, well, here's your box, and here draw a slope. We're talking about the slope. c0 times the slope, plus c1 times the slope of a linear term, right? Plus c2 times the slope, make sure I put this, plus c3 times the slope. We want the slope of each of these. The slope, there are different slope factors that apply to a T3 than a T2. A T3 has a C3, which we found out was 3. 3 times this diagonal slope of this function. Here, that's a second order term. It's 2 times, C2 is 2 times the diagonal. Here, C1, that's just 1 times, and C0 is 0 times. So you can kind of see an interesting relationship between these slopes and these areas. Here the slope, we actually lower by 1 degree because it's f of x over x. Let's just look at it just briefly. Okay, let's say I draw it like this. And we have y equals x to the n, and you have some point over here. Well, its value is x to the n. You see it? This is on the x-axis, right? This is f of x. Well, box it means put a box around it, just like this. And also draw the diagonal. See it? That's what we're doing when we're doing these boxes. When I say think inside the box, this is what I'm talking about. That we have this parametric equation, and this point can go anywhere from here, from 0 to, wherever. So x to the n. And the area, what we're saying, is this box. So you have to take x times x to the n, your base times height, times an appropriate k factor, which will be different for each number. For a triangle, which is power 1, it's 1/2. For a second order equation, it's 1/3. And we're going to find out what it is. Well, we already know it's going to be there. It's going to be 1/4 for K3. This is what I mean, box it and draw a diagonal. The area you raise by 1 power. It's essentially area equals K sub n times the box, the area, which is x to the n times x. See it? That is a box. That's that concept I'm trying to teach you. The slope, tangent slope, equals c sub n. Again, these are all invariants, by the way. They don't change. They're fixed for a particular order. What is that? X to the n divided by x. And just, again, put a box here. See how I'm unboxing it? I'm talking about this slope. This is what I'm talking about. Take x divided by x to the n divided by. So you've lowered it by 1 degree. Multiplied by an invariant. You got the slope. For area, similar, but you raise by 1 power, multiplied by x. X to the n times x. Times the invariant k sub n, which is different for each n. So that's where we're headed. And our job is to find out really what is k sub n and c sub n, which we already know. C sub n is n. K sub n, well, we're getting there. Okay, so with this in mind, these boxes, these slopes, let's continue. And here we have, okay, so K3, this big wedge, and it's a 1 plus c third times 1 plus c. So it's really K3 1 plus c to the 4th power equals all of these little areas. 4 of these, and then the 5th one is this one. See it? And that's what they look like. Okay, so we're going to have to crank this out. K3 equals 1 to the 4th, that's 1, plus 1 to the 3rd times c. Excuse me, but it's got to be multiplied by a factor of 4. See it? Plus 1 times c squared plus a factor of 6. C squared plus 4 c third plus c to the 4th. Okay. And that equals, well, that equals K3 plus c plus 3/2 c plus c squared plus, what is this? Am I doing it right? C squared, I'm making mistakes. C third plus K3 c to the fourth. All right. I think I got it. They should be increasing. C squared, C third, C to the fourth. All right. And look for things that cancel out. So we have K3 times 1, K3 times 1. That cancels out. Gone. And we also have that the bounds, first term and the last term, will always cancel out. K3 times C to the fourth. Well, that's out. That's out. Okay. What we have left are terms that contain C squared, and C third. All right? C squared, and C third. Now let me just rewrite it for you in a way that it may make more sense. We got K3 times 4C plus K3 times 6C squared plus K3 times 4C to the third. All of that equals, right? On this side equals this side. What is that? Well, just rearrange it. So, it's okay. I'm doing it so that you can easily see it. Well, that's C. That's 3/2 C squared, and that's C to the third. Well, look at what we have. Collect your C's, collect your C squared and C thirds. You treat them separately. And look, from here you can see that C cancels C. From here you can say K3 times 4C equals 1C, right? And that immediately gives us K3 equals 1/4, which we kind of knew already, right? All right, that's good. What about this one? You got K3 6C squared equals 3/2 C squared. The C squared goes away. And so you got 2 times 3, and 3/2. Well, that 3 is going to cancel the 3, and the 2 will end up here, and you got, again, 1/4. You see it? That's an easy one to solve. So it's a redundant information, but it matches. Again, K3 equals 1/4. That's good. K3 equals 1/4. What about this term? I think it looks the same as the top one, except you're collecting C thirds. K3 4C third equals C to the third. C thirds cancel out. Immediately you got K3 equals 1/4. They are in agreement. This is redundant. It's not really necessary. You can throw it away. And essentially, this is the approach that we're going to take when we take it to, x to the n. There are going to be a bunch of redundant terms that get thrown away. The only one that matters is this one, which will really be K3 times n, C equals C. And so from that, we will find that K sub n equals 1/n plus 1. Remember? This is a third degree, and so this one is n plus 1. that pattern is going to repeat. We'll do that in my next video, but this is just a precursor, a warm-up, a heads-up that we're headed that way, and that there are these terms that are redundant, and so for most of this stuff you can throw away. You don't care about it. The only one that matters is this one. These two always cancel out at the bookends, and this one is the one that matters, this one here, and this one, right? These two terms, right? This other stuff, that's nice to know, it's all redundant stuff. Now there's C terms, C squared terms, C third terms, very nice, but doesn't give us any new information. K3 is 1/4, K3 is 1/4, thank you, we don't need you, goodbye. The only one we need is this one. And for y equals x to the n, this is going to be an n. K3 times mc is equal to c. Immediately we get this. So heads up, this is Cavalieri's formula, and not just for 1 to 9, but from 1 to n. Really great stuff. And in addition, we're also looking at slopes and areas, and we're looking at them at once, simultaneously. You're seeing them right before you, and you're seeing this relationship that with slopes, well, the diagonal, okay, you lower by 1 degree power. Here with areas, you raise it by 1 degree. So they are inverse. They are inverse. And that's something fundamental. Really fundamental, and we'll get to that. We'll have a video just for that fundamental nature. There's a special term called fundamental theorem. What could it be? Oh well. Anyways, we're going to sign off at this point. So as Professor Theoremus Antiquitus would say, let's see, before there was calculus, there was quadrature. You got it! Let's roll it!